This question is about weak acids. The Ka values of 3 weak acids are shown in table 20.1. Part A. Calculate the pH of 0.0800 moles per decimeter cubed C2H5COOH aqueous. Give your answer to 2 decimal places. For this question, we're going to use multiple equations. The first equation we're going to use is Ka equals A minus multiplied by H plus, and this is all going to be over HA. So this is the general equation. And what we're going to do is assume that the concentration of A minus equals the concentration of H plus, and we can have H plus squared over HA. And that means we can then rearrange to work out H plus. So we're going to work out H plus. Our concentration of HA, or our acid that we're going to work out, is 0.08. And our Ka value is 1.35 times 10 to the negative 5. So that means 1.35 times 10 to the negative 5 equals H plus squared over 0.08. So then we can rearrange to work out H plus squared by multiplying across our 0.08. So that means that our H plus squared equals 1.08 times 10 to the negative 6 moles squared decimeters to the minus 6. Then to get H plus on its own, we need to root this answer. So H plus equals the square root of 1.08 times 10 to the negative 6, and that equals 1.04 times 10 to the negative 3 moles per decimeter cubed. Then we're going to use another equation. The equation we're going to use is that pH equals minus log 10 of the concentration of H plus. And that's what we're going to use to work out our pH value, and we're going to give our answer to 2 decimal places. So pH equals minus log 10 of 1.04 times 10 to the negative 3, and that equals 2.98 to 2 decimal places, and that's what we're going to write on the answer line for this question, 2.98. To get the 2 marks for this question, you get a mark for working out the concentration of H plus correctly, so 1.04 times 10 to the negative 3 moles per decimeter cubed, and you get a mark for correctly working out your pH to 2 decimal places, so 2.98. Part B. A student adds a total of 45 centimeters cubed of 0.1 moles per decimeter cubed NaOH aqueous to 25.0 centimeters cubed of 0.08 moles per decimeter cubed C2H5COOH aqueous and monitors the pH throughout. Part 1. Show by calculation that 20 centimeters cubed of NaOH is required to reach the end point. Firstly, with this question, we're going to use the equation triangle NV times C, where N is number of moles, V is volume, and C is concentration. We're going to first work out the moles of C2H5COOH. So we're going to use 25 centimeters cubed and 0.08 moles per decimeter cubed. So we're going to do 25 times 10 to the negative 3, because we've converted centimeters cubed into decimeters cubed, multiplied by 0.08 moles per decimeter cubed, and that equals 0.002 moles of C2H5COOH. Then we're going to use these moles to work out the volume of NaOH. Now we're told in the question that we're using a concentration of 0.1 moles per decimeter cubed. So we can work out volume by doing 0.002 divided by 0.1, and that equals 0.02 decimeters cubed. But we're told we're using 20 centimeters cubed. and so we need to times by 1,000 to get centimetres cubed, and that would give us 20 centimetres cubed, which matches what we're given in the question. To get the mark for this question, you must show that you need 20 centimetres cubed by doing the working as I've done now. So working out the moles of C2H5COOH, and then using these moles to then work out the volume of NaOH that you use. This gets you the mark for the question. Firstly, we need to highlight the key pieces of information. So that's the volume and concentration of NaOH and the volume and concentration of C2H5COOH, and the fact we have to work out pH to 2 decimal places. So we're going to be using the equation triangle firstly of NV times C. And what we're going to do is we're going to work out the number of moles of OH minus that are in excess. And that's equal to the number of moles of OH minus subtract the number of moles of C2H5COOH. And by doing this, what we're doing is working out how much sodium hydroxide, or NaOH, is used in the equation with C2H5COOH, and how much is left over or is in excess, because the student is adding more NaOH, so an excess of NaOH to this reaction. So by working out the moles of OH minus in excess, we can then use this to work out pH. So using the equation triangle, we would have 45 times 10 to the negative 3 times 0.1, so that's volume times concentration, and that equals 0.0045 moles of OH minus ions. Doing the same for C2H5COOH, that'd be 25 times 10 to the negative 3 multiplied by 0.08. So that's volume times concentration, and that equals 0.002 moles. So that gives us the number of moles of OH minus in excess, and that is equal to 0.0045 minus 0.002, and that equals 0.0025 moles. Then the next equation we're going to use is this same equation triangle but rearranged, because we want to work out the concentration of OH minus. So that's the number of moles divided by volume. So it's going to be 0.0025 divided by 70 times 10 to the negative 3. The 70 is because we've got 45 and 25 centimetres cubed. So 45 plus 25 equals 70 centimetres cubed, and we want decimetres cubed, so we've timesed by 10 to the negative 3. And that equals 0.0357 moles per decimetre cubed. So our next equation we're going to do to work out pH, but firstly POH, and that is equal to minus log 10 of the concentration of OH minus. And then we know that 14 is equal to POH plus pH. So 14 minus POH equals pH. These are the two equations we're going to use to find pH. So firstly, working out POH, that's going to be negative log 10 of 0.0357, and that equals 1.447. And then 14 minus 1.447 equals 12.55 to 2 decimal places, which we then write on the answer line provided, 12.55. To get the 4 marks for this question, you get a mark for working out the number of moles of OH minus in excess, so 0.0025 moles. You get a mark for working out the concentration of OH minus correctly, so 0.0357 moles per decimeter cubed. You get a mark for working out POH, so 1.447, and then you get a mark for working out pH, so 12.55. Part 3. On the axes below, sketch a pH curve for the pH changes during the addition of 45 centimeters cubed of 0.1 moles per decimeter cubed NaOH aqueous to 25.0 centimeters cubed of 0.08 moles per decimeter cubed C2H5COOH aqueous. So this is the pH curve of a strong base, weak acid titration. So that means our pH is going to start at around 3. We're going to have our 2.98 start. And then at about 20 centimeters cubed, we're going to start seeing our vertical section. And this is going to level off. So this is roughly what our curve would look like, with our equivalence value above pH of 7 because we've got a strong base, so that means, and a weak acid, so that means our equivalence value is going to be greater than 7. And we're starting at a weak acid pH because we're not starting at a 1, we're starting at around 3, and we're leveling off at around 13, which is showing that our strong base. To get the marks for this question, you get a mark for having a slight rise / flat and near vertical, and then a slight rise / flat. So this is the general pattern of a flat area, a sharp increase or incline, and then a flat area on our graph. Then for the pH, the vertical section with extremes of pH of 5 to 12 and a minimum range of 3 pH units, which we've got here. We're starting at 3 and we've got extremes in the vertical section of 5 and 12. Then we need a middle section of the vertical section, and it needs to be above our pH of 7. And this is what I was talking about with the equivalence point. So our equivalence point is around here, and as we can see, this is about 8, but this is just a rough estimate, but it is above 7, so that's fine. And then for our end point of the vertical section, it needs to be around 20 centimeters cubed, which is why we have it here. Following down, we've got 20 centimeters cubed. So that's a mark for the general shape, a mark for the pHs of our shape being correct, and a mark for having your end point at a volume of 20 centimeters cubed, the end point of the vertical section. Part 4. The student considers using the 4 indicators in table 20.2 for the titration. Explain which indicator would be most suitable for the titration. So for this titration, Cresol purple would be the most suitable indicator, and that is because the pH range matches the vertical section or the equivalence point, because our equivalence point is above 7 or above a pH of 7, and the Cresol purple pH range is 7.6 to 9.2. So this is perfect for what we need for this titration. To get the mark for this question, you must say Cresol purple and then give a reason why. So the reason why would be because the pH range matches the vertical section or equivalence point. Both these terms are accepted for this mark. Part 5. The student repeats the experiment starting with 25 centimeters cubed of 0.08 moles per decimeter cubed HCN and adding a total of 45 centimeters cubed of 0.1 moles per decimeter cubed NaOH. Predict one similarity and one difference between the pH curve with C2H5COOH and the pH curve with HCN. Use the information in table 20.1 and your answer to be part 3. A similarity would be that the end point of NaOH needed to neutralize. So that would be the volume of NaOH needed to neutralize HCN, and C2H5COOH is the same. but a difference is that HCN has a higher starting pH. To get the 2 marks for this question, you get a mark for your similarity and a mark for your difference. The reason that the end point of NaOH needed to neutralise is the similarity in this case is because of the volume and concentration of NaOH needed being the same and the volume and concentration of HCN being the same. That's why the end point of NaOH needed to neutralise the HCN is the same. Part C. The student calculates the pH of 0.08 moles per decimeter cubed HiO3 aqueous. The student assumes that the equilibrium concentration of HiO3 aqueous is the same as the initial concentration of HiO3 aqueous. The student measures the pH and finds that the measured pH value is different from the calculated pH value. Explain why the measured pH is different from the calculated pH. For this question, there are multiple answers as to why the measured pH is different from the calculated pH. So I'm going to write them as bullet points. Our first bullet point is that HiO3 dissociation is not negligible. This would get you a mark for the question. But also you could say a large Ka and HiO3 is a stronger weak acid. This would also get you the mark for this question. Alternatively, you could say that HiO3 at equilibrium, the concentration of HiO3 at equilibrium, is significantly lower than the concentration of HiO3 initially, or when it's undissociated. So to get the mark for this question, you could say any of these statements or any of the bullet points that I've listed in this question. So if you were unsure, you can make a revision resource of these 3 bullet points because they could be transferable in a similar question. The reasoning behind this question and why the pH value is different from the calculated pH value is, for example, if the concentration of HiO3 at equilibrium is lower than initially, that means it's going to be less acidic, or it's going to have a higher pH at equilibrium than initially. And that fits with our second bullet point of a stronger weak acid. So a weak acid is going to have a higher pH than a strong acid.